Hello everyone. We have started this photochemistry course, and in the previous lecture we have mentioned some basic aspects of photochemical reactions. We also mentioned that when we are talking about photochemistry, which light is important, how much amount of energy you are dealing with, and when you give this much amount of energy in terms of light to a molecule, what changes takes place in the molecule goes to an excited state. These excited states are high energy species and short lived. They can undergo different photophysical processes like radiative, non-radiative processes, or may undergo different photochemical reaction. These different photochemical reactions depends on the type of chromophore present in the starting molecule. We have also mentioned that this photoexcitation can be brought about either by direct photolysis as well as by indirect photolysis. In direct photolysis, molecule absorbs the light, goes to an excited state, and then they can undergo different photoreaction. In indirect photolysis, a second molecule is used which is known as sensitizer. This sensitizer absorbs light, goes to an excited state, and it can transfer energy and then come back to ground state, or these and the molecule which accepts energy can further undergo different reactions. These indirect photolysis can be of two types, either by energy transfer, or it can also be an electron transfer. So, photo-induced electron transfer reactions are also known in these reactions, where the sensitizer can have we have two molecules, donor and acceptor. Donor gives an electron to acceptor, and then it can form radical cation and radical anion species, and they can further undergo different reactions. These photo-induced electron transfer reactions are once again of two types. We have mentioned in the previous lecture: homogeneous photo-induced electron transfer as well as heterogeneous photo-induced electron transfer. In homogeneous electron transfer, donor and acceptance both are soluble as a single phase reaction, whereas in heterogeneous electron transfer reaction, it is a biphasic reaction where the one component is insoluble and reaction takes place on the surface of the reaction. We have also mentioned an example of this heterogeneous photo-induced electron transfer taking a semiconductor mediated photoreaction, where there is a which is divided by which is characterized by filled valence band and vacant conduction band. And these the electron on excitation, when we shine light of energy equal to band gap, can go to electron can go to valence band, conduction band, and then there is a hole generating valence band, and then they can, in other words, we generate oxidation reduction sites on the surface of the reaction. Today, in continuation to our on this lecture, what we are as far as photochemistry is concerned, there are two basic laws in photochemistry. One is the Grothes-Draper law is the first law of photochemistry, which describes principle of photochemical reaction. According to this law, only that radiation which are absorbed by reacting substrate can be effective in producing chemical changes. Reflected and transmitted light does not produce any chemical change. This is the first law given by Grothes-Draper. Say, for example, if you have a two reactant A and B, and when we shine light, the light absorbed by the reactant is converted to product P, and reflected and transmitted light do not undergo any photochemical change. The absorbed light can be further calculated according to this equation: I absorb equal to I instant light minus I transmittance. A second law is given is known as Stark-Einstein law, the second law of photochemistry, and it states that one quantum of radiation or energy h nu absorbed by a molecule activates one molecule of substrate. Say AB is a reactant and absorbs one quantum of light leads to product A plus B. One molecule absorbs one photon to transform into one product. Per molecule, per photon, N is the mole of reactant absorbed and N is the mole of photon. So then E is equal to h nu or hc by lambda. Energy absorbed per molecule is obtained by multiplying the above expression by Avogadro number. So this is the expression to E is equal to h nu is equal to 1 Einstein and hc by lambda. Going further to in the basic principle involved in photochemical reaction, as far as photochemical reactions are concerned, depending upon the potential energy curve of ground state and potential energy curve of excited state, the photochemical reactions are of three types, or we can say that they are classified into three different types based on the potential energy, the movement of the reactant to the product from ground state curve to the excited state. These they are categorized as adiabatic photochemical reaction, non-adiabatic photochemical reaction and hot ground state photochemical reaction. The next few slides I am going to explain how these three types are explained graphically, and it is self-explanatory. So this is the first type. This is adiabatic potential energy curve of ground state. So this is there are two curves. This is the ground state curve and this is the potential energy curve. We have a reactant in the ground state which on absorption of light goes to an excited state of the reactant. So that is ESR is the excited state of the reactant. The reactant in the excited state moves on the surface of the excited state curve and then goes to transform into product P star, the excited state of the product. Now this loses light h nu star and comes back to product in the ground state. So when this type of when the reaction proceeds like this, these reactions are known as adiabatic photochemical reaction. A second type of photochemical reaction can be further explained accordingly. This is the second type, non-adiabatic photochemical reaction, where as usual we have the ground state curve, we have a excited state curve, ES is excited state curve, GS is the ground state curve. This is GSR is the reactant in the ground state, on absorption of light goes to the reactant in the excited state. ESR, reactant in the excited state. The reactant in the excited state moves on the surface of the excited state curve. In this type of photochemical reaction, the both ground state and excited state curve to some extent very close to each other, and then there is a formation of funnel, and then there is a switch over of the excited state curve to the ground state, because they are very close to each other, and then excited state curve comes to the ground state curve and rest of the reaction takes place on the surface of the ground state. But here there are two possibilities. The excited state reactant can come back to ground state reactant, or it can proceed further to the product. So this type of reactions are best example by photochemical cis-trans isomerization of alkene, where more stable trans isomer can be converted to less stable cis isomer, since and it is not possible to proceed 100% conversion because they are in equilibrium, and this is the reason why and this is a special, it can be categorized as a non-adiabatic type of photochemical reaction, which is a cis-trans isomerization of alkene. Third type of photochemical reaction can be represented via this reaction, where you can see here, as usual, we have a ground state curve, we have a excited state curve, we have a reactant R in the ground state, we have a reactant excited state, reactant in the excited state. So reactant on absorption of light goes to an excited state and then proceed further, and then here also there is a switching over of the excited state reactant to the ground state curve of the ground state curve, and then there is a formation of an intermediate I, and then the energy barrier for this intermediate is very less, and hence it can overcome very easily, and then it can proceed to the product. So this is a third type of photochemical reaction, that is hot ground state photochemical reaction, where there is the involvement of an intermediate I. In the next slide, all these three types of photochemical reactions have been represented. So as usual, we have three types: adiabatic photochemical reaction, diabatic or non-adiabatic photochemical reaction. Third type is hot ground state. So in adiabatic, we have a reactant on absorption, it goes to R star, then proceed to excited state of the product and come back to product in the ground state of product by losing the light, either in the form of fluorescence and phosphorescence. Non-adiabatic and diabatic photochemical reaction, R on absorption of light goes to R star and then come back to product, that is switching over to the ground state curve. Third type is the involvement of intermediate I, and then this intermediate I has a very small barrier, can proceed to the product P. See, again, all these three types have been represented graphically. Going further to this lecture, the one of the most important aspects in these reaction or any chemical reaction, people talk about the yield. What is the yield of the product? So in the case of photochemical reaction, this is represented as how efficient the photochemical reaction is represented by the quantum yield phi, and it is represented by the number of moles of reactant consumed or product formed in a given time t divided by the number of moles of photon in terms of Einstein absorbed during the same time. So and the reactant consumed or product formed can be determined by any analytical method like GC, HPLC, and then we can determine how much reactant had produced, how many reactant has consumed or product formed. So the first parameter can be determined by any analytical tool, whereas number of moles of photon absorbed can be determined by a method called actinometry, and determined by any and this is there are a few standard actinometers are reported in the literature, which is I am going to take up this in a few slides. If the quantum yield, if each photon absorbed produces one molecular transformation, then the quantum yield is unity. It is less than, it is more than 1. If the quantum yield is more than 1, is less than 1, then other process of deactivation reaction takes place. And if the quantum yield is more than 1, then the change reaction has been initiated by the primary product formed in this reaction. As I have mentioned, the quantum yield, I mean the number of photons absorbed can be determined by can be evaluated by actinometer. The two representative examples of actinometry are represented. First one is potassium ferrioxalate actinometry, which involves the net reaction is 2Fe3 plus C2 that is oxalate in the presence of light gives to Fe2 plus with the evolution of carbon dioxide. And then this actinometry experiment is to be carried out in the same photochemical reaction vessel in which the photochemistry of any organic compound is determined, because the glass is very important, the thickness, the length, width, and so on and so forth. So, actinometry experiment has to be carried out in the same glass equipment where photochemistry of any organic compound is determined. The second actinometer is the uranyl oxalate actinometry. The net reaction involved here is H2Cr2O4 in the presence of light, giving rise to water, CO2 and carbon monoxide. The uranyl ion acts as a photosensitizer to the decomposition of oxalate ion. The amount of oxalate ion before and after the measurement is determined by titration with K-4. So, these are few standard actinometry experiments are available in order to determine the quantum yield of any photochemical reaction. As I have mentioned, the reactant consumed or product form can be used by GC, HPLC or GCMS as well, or whereas actinometry can be represented by can be determined by these two representative actinometers. And by after doing this experiment, the I, that it is the Einstein per minute, can be determined by A is the absorbance, and these are different parameters which we can put up and then find out how much is the I, that is the this particular parameter, and then we can determine what is the quantum yield of any photochemical reaction. So far we have been discussing about the photochemical basic principle involved in photochemistry, the type of photochemical reaction, how to determine the quantum yield of any photochemical reaction. These are the standard the method to determine actinometry, but there are more sophisticated instrumentation techniques are available to determine I by photometer. Just put the photometer in front of lab, and then it determines how much I is falling on your photoreactor, and then it is possible to determine the quantum yield. Now onwards in the follow-up lecture, now I am going to concentrate more on organic photochemistry, the different photochemical reaction exhibited by different chromophore such as alkene, carbonyl compounds, alpha beta unsaturated compounds, aromatic compounds, some named photochemical reactions, and so on and so forth. So this slide shows the photochemistry of alkene. The basic photochemistry involved in alkene is the cis-trans isomerization, and we are also going to discuss the photochemistry of 1,4-diene as well as 1,5-diene, because 1,4-diene undergoes very interesting photochemistry in this. So as far as photochemistry of alkene is concerned, cis-trans isomerization is a typical photoreaction of many olefinic compounds. They are promoted by direct photolysis as well as indirect photolysis, as I have mentioned, which can in the previous lecture that we can do by sensitized photolysis as well, means by using a sensitizer. So, in some simple alkene, the E isomer, that is the trans isomer, which is more stable, the absorbs at different wavelength, and hence it is possible to convert more stable E isomer to less stable Z isomer. And then in the coming few slides, I am going to concentrate on the photochemical reactions of few representative organic compounds. Now, this is the trans alkene. You have a substituent X on the opposite side. In the presence of light, the alkene absorbs light, goes to an excited state. Mainly the cleavage of carbon-carbon double bond takes place, is a diradical species, and there is the loss of carbon-carbon double bond. In this starting material, due to the presence of double bond, the free rotation is restricted. Now, on absorption of light, when it goes to a diradical species, the loss of double bond leads to a diradical intermediate. Now, there is a possibility of free rotation of this bond, and then it can this trans isomer can go to cis isomer, and then all these reactions are always in equilibrium, the K trans for this transformation, and then this radical once again can combine to give you a cis isomer. This again, this is, as I mentioned, this is a typical example of the what we call is as a non-adiabatic photochemical reaction, where the hot ground state, the excited state of the potential energy curve of ground state and potential energy curve of excited state are very close to each other, and then the excited state reactant can switch over to ground state, and then there is a always in equilibrium, and the reactant can come back to ground state, or it can proceed to the product. So, this is a simple schematic representation of photocatalytic cis-trans isomerization of alkene, where a trans isomer is converted to cis isomer. The trans isomer on absorption of light goes to an excited state, which leads to a loss of double bond character, formation of a diradical species, free rotation possible, and then the coupling of this radical can lead to cis isomer. This slide shows the few representative examples of cis-trans isomerization of alkene. The fumaric acid can be transformed to malic acid in the presence of light. This is again an example of photochemical cis-trans isomerization. Another examples of photochemical cis-trans isomerization is the trans-stilbene, trans-alkene. In the presence of light can go to cis-alkene, and again it is in equilibrium. And a third example of photochemical cis-trans isomerization is azobenzene. A trans form can be converted to cis form in the presence of light. This is another the cis-trans isomerization followed by cyclization. As usual, you have a trans-stilbene in the presence of light can goes to cis-stilbene, and then this cis-stilbene, if you continue irradiation, and then if we can represent these two phenyl groups in this form, on prolonged irradiation, this can further undergo cyclization via 6-2-2-2, 6 pi electron cyclization to give you a dihydrophenanthrene. So, this is a 2 photon reaction. One photon is involved in conversion of trans to cis, another photon is involved for 6 pi electron photochemical cyclization to dihydrophenanthrene type derivative, and then this can open up thermally go back to the starting cis-still bean. This dihydrogen derivative is can be very easily or susceptible to undergo air oxidation to give you a more stable aromatic compound phenanthrene. So, this is the example of a cis-trans isomerization followed by cyclization. If the molecule in the cis isomer is suitably substituted, which can undergo 6 pi electron photochemical cyclization. So, this in the presence of light can lead to this type of reaction. Few examples of similar reactions are also shown in the next slide. So, this is an example of a trans or a trans alkene. You have a phenyl group at one end and you have a thiophene at the other end. In the presence of light can undergo cis-trans isomerization. Of course, it is in equilibrium. Cis isomer can further undergo 6 pi electron cyclization photochemically, 2 electrons here, 2, 4, 6 photochemical 6 pi electron cyclization to give you dihydro derivative, and then it can further aromatize. So, this is the photochemical reaction. You do not need any light for this aromatization, and then this can be brought about any catalytic or air oxidation method. A few more examples of more important reactions involving cis-trans isomerization followed by cyclization is also shown over here. You can see an E isomer, techisterol is a steroid derivative in the presence of light can undergo cis-trans isomerization across the double bond. So, you can have a this bulky substituent on the cis orientation, and then you can see very carefully this is again nicely set for 2, 4 and then 6 pi electron cyclization in Z isomer. This is a pro-vitamin D2 under photolytic condition can undergo 6 pi electron cyclization to give you a lumisterol, a cyclized steroid derivative. So, it is not necessary that we should have a 2 aromatic rings as in the previous case for this type of reaction. Even cyclization, you need to have a 3 double bonds nicely oriented in cis fashion, so that it can undergo 6 pi electron cyclization to give you a lumisterol. So, this is another example of synthetically important techisterol going to provitamin D2 via cis-trans isomerization photochemical. Once again, provitamin D2 may undergo 6 pi electron cyclization under photochemical method to give you lumisterol, which can thermally lead to vitamin D2. This is another example of cis-trans isomerization. We have a dibenzoyl, 2 benzoyl group in cis orientation, in trans orientation is a trans dibenzoyl alkene in the presence of light can also undergo cis-trans isomerization to give you a cis dibenzoyl alkene. Now, again 2 benzoyl group in the cis isomer is again nicely suited for a further photochemical reaction, and then is a interesting photochemical reaction by this 2 benzoyl group oriented in cis fashion is shown over here. Here what happens, we have just represented this benzoyl by a carbonyl C6H5. This carbonyl can be represented like this, and then again another benzoyl group. The excited one of the this is in the presence of light. The carbonyl goes to an excited state. This excited state can add to the phenyl group at this position to give you give you a cyclized intermediate as dipolar species, and then which can once again open up O minus. So there is a cleavage of this bond. This bond cleavage takes place, and then to give a ketene derived intermediate, and we know that the ketene derivative is highly unstable, and then it can undergo can give different products like a carboxylic acid in the presence of water, or it can give an ester in the presence of methanol. So these rearranged products are known to be formed when we have dibenzoyl alkene in the cis orientation. This is what we can essentially see here is the phenyl group migration. So you can see phenyl group from one benzoyl is migrated to this via decomposition of this intermediate, and you can see this becomes OCCH5, and then this ketene can becomes either an ester or an acid at this end. So this is another interesting rearrangement of cis-trans isomerization of alkene, followed by the phenyl group migration. So you can see here the cis-trans isomerization followed by cyclization. We can also see here cis-trans isomerization followed by phenyl group migration. So if we have a proper substituent in the cis orientation, although the reaction is reversible and cis isomer is unstable, I mean it is less stable than trans isomer, it can further undergo photochemical reaction to give the cyclized dihydrophenanthrene in this particular case, or a carboxylic acid phenyl group migrated, or an ester derivative phenyl group migrated in this product. So I stop here. Thank you very much.